The Opposing View Podcast. Asteroid Impact. Are we prepared for the ultimate black swan? Welcome to The Opposing View, the show where conflicting perspectives collide, not for spectacle, but for substance. Today's topic takes us far beyond the everyday and into the cosmic unknown. Asteroid Impact. Are we prepared for the ultimate black swan? Asteroids, relics of our solar system's formation, have shaped our planet's history more than we like to admit. From the extinction of the dinosaurs to the surprise detonation over Chelyabinsk in 2013, space rocks have an unsettling habit of reminding us that Earth is not immune to outside forces. But here's the question. If one were headed our way today, would we know in time? Could we stop it? Or are we simply hoping that it won't be our turn? To explore this, we've invited two experts, both seasoned analytical thinkers with very different views. Expert Introduction. First, we have Dr. Richard Kehl, a physicist specializing in orbital dynamics and kinetic deflection systems. Over the past 20 years, he has contributed to both public and classified simulations on planetary defense, and he currently focuses on integrating AI-driven tracking with early intervention capabilities. Opposite him sits Dr. Stephen Langford, a systems theorist and geophysicist. He studies the vulnerability of complex civilizations to external shocks with a focus on low-probability, high-impact scenarios. His research includes historical collapses and modern fragility under stress, from pandemics to geomagnetic storms to cosmic events. Dr. Richard Kehl, Opening Argument.
Thank you. Let me begin with a fundamental truth. Planetary defense is no longer science fiction, it's operational reality. For decades, humanity was in a reactive stance, simply observing the sky. But today we're shaping the risk environment. In 2022, NASA's DART mission marked a turning point. We deliberately altered the orbit of a celestial object. The asteroid moonlit Dimorphos, orbiting Didymos, was hit by a kinetic impactor that changed its trajectory measurably, not in theory, but in verifiable data from telescopes on Earth and in space. This wasn't a stunt. It was a demonstration that we can intervene in the cosmos. The European Space Agency's Hera mission, scheduled for launch in 2027, will follow up with detailed measurements. This is incremental, testable progress, not wishful thinking. Now, let's talk about detection. As of mid-2025, over 32,000 near-Earth asteroids have been catalogued, and for those larger than 1 kilometer, the truly catastrophic ones, we have mapped over 95%. Instruments like Pan-STARRS, ATLAS, and soon NEO Surveyor are constantly scanning the sky. Pan-STARRS alone discovers several dozen new NEOs each month. And contrary to common fear, space is not infinite chaos. Asteroid orbits follow physical laws. With current AI integration, we can simulate impact probabilities decades in advance. In fact, teams at MIT and ESA are working on autonomous early warning systems that would issue alerts and launch options without human delay. We're not betting on luck. We're building tools, protocols, and muscle memory. Every year improves our detection range and reaction time. This is a textbook example of how civilization learns from risk.
A powerful argument for rational optimism, that technology and coordination are moving us away from helplessness. But how robust is that optimism? Let's hear from Dr. Langford. Dr. Stephen Langford, Opening Argument.
Thank you. While I appreciate Dr. Kehl's technological clarity, I believe he fundamentally underestimates the nature of systemic fragility. Let me say this outright. The idea that a few successful missions and expanding asteroid catalogs make us prepared is deeply misleading. What we are doing is managing visibility, not eliminating existential risk. Yes, DART worked, but that test occurred under perfect conditions. Ideal timing, known target, zero political friction. Try doing that under duress with a 6-month warning during a global diplomatic crisis, or worse, with no warning at all. Take the Chelyabinsk explosion in 2013. This event occurred over Chelyabinsk Oblast, a heavily populated region in southwestern Russia near the Ural Mountains. The asteroid was roughly 20 meters in diameter and weighed an estimated 13,000 metric tons. It entered Earth's atmosphere at around 19 kilometers per second, over 50,000 kilometers per hour, and approached from the direction of the Sun, an observational blind spot where ground-based telescopes cannot effectively detect incoming objects. At about 30 kilometers above the ground, it exploded with an energy yield of 400 to 500 kilotons, roughly 20 to 30 times the power of the Hiroshima bomb. The explosion created a blinding flash and a shockwave that shattered windows, damaged buildings across 6 cities, and injured over 1,600 people, mostly due to broken glass and structural debris. Thankfully, the angle of entry was shallow. Had it come in steeper or exploded lower in the atmosphere, thousands, possibly tens of thousands, could have died, given the area's dense population. Now let's go further back to the Tunguska event in 1908, which struck a remote area near the Podkamennaya Tunguska River in central Siberia, Russia. On the morning of June 30th, an object believed to be an asteroid 50 to 60 meters across entered the atmosphere and detonated in an airburst at 5 to 10 kilometers altitude. The explosion was equivalent to 10 to 15 megatons of TNT, comparable to the largest thermonuclear weapons ever tested. The blast flattened 2,000 square kilometers of Siberian taiga forest, snapping over 80 million trees like matchsticks. Witnesses reported a bright flash and heat wave felt hundreds of kilometers away. Though no crater was found, confirming a mid-air explosion, the sheer devastation left behind was unprecedented for a natural event in recorded history. Fortunately, due to the remoteness of the location, there were no confirmed human fatalities, but had it occurred over a city, it would have resulted in massive loss of life. And what if we do detect one? What if we spot an object with a 70% impact probability and 6 months to go? Here's what happens. First, doubt. Scientists will argue over trajectory models, then delay. Politicians wait to confirm the threat. Then denial. Media spin and public panic override rational planning. Then dysfunction? Who pays? Who decides? Who launches? NASA and FEMA ran this exact simulation in 2020. The outcome? No coordinated plan, no authority structure, no clarity. The report concluded that, in the event of a real impact, confusion is likely to hamper the response. Asteroids are a black swan not just because of low probability, but because of high complexity. We do not live in a world where action follows detection in straight lines.
Rebuttals. Two experts, two very different interpretations of our readiness. Dr. Kehl, how do you respond to Dr. Langford's concerns? Rebuttal 1. Dr. Richard Kehl.
Let me first say that I agree with one premise in Dr. Langford's argument. Detection without coordination is not enough, but that's precisely why coordination is happening. After Chelyabinsk, the international response was swift. By 2015, the UN Committee on the Peaceful Uses of Outer Space, COPUOS, recommended the formation of the International Asteroid Warning Network, IAWN. It's a real body with real protocols coordinating space agencies from the US, Europe, Japan, and beyond. We're not in the Wild West anymore. In fact, the 2023 Planetary Defense Conference in Vienna included multilateral simulations involving over 60 countries. The scenario involved a 400-meter asteroid on a high-probability impact course. Result? Joint strategies emerged within 72 hours. Evacuation plans were drafted. Potential deflection missions were assessed. Yes, Tunguska was devastating, but that was over a century ago. Pre-radar, pre-satellite, pre-space age. Today, even a 50-meter object like Tunguska would likely be spotted weeks to months ahead, especially with NEO Surveyor launching in 2027, which is optimized for sunward detection. As for the 2020 FEMA simulation, it was meant to expose weak points. That's what drills are for, and those gaps are already being addressed. To portray all this as a naive belief in technological salvation is unfair. It's not belief, it's data, funding, international cooperation, and a decade of successful iteration.
A confident counter that past failures are precisely what current systems are designed to prevent. Dr. Langford, your response? Rebuttal 2. Dr. Stephen Langford.
Richard, I respect the progress, but your rebuttal confirms my deeper fear. We are equating procedural improvement with actual resilience. You cite conferences and networks. That's good, on paper. But I would urge listeners to look at real-world stress tests, not simulations. Remember COVID-19? The world had pandemic preparedness plans. World Health Organization had protocols. Every major nation had scenario documents. When the virus hit, those plans collapsed under pressure. We saw supply chain breakdowns, medical rationing, policy paralysis, and national hoarding, even between allies, and COVID gave us months to respond. An asteroid impact could give us days. Let me give you a number. In 2019, the B612 Foundation estimated that there are over 1 million NEOs larger than 30 meters, of which only 1 to 2% have been discovered. We are still essentially blind to small and mid-sized threats, the same ones most likely to explode over cities. We may win the next encounter, or we may have a 10-megaton airburst over Lagos, Jakarta, or Sao Paulo, and we'll tell ourselves it was unexpected. Again.
Closing remarks. From interagency simulations to airbursts over Russian skies, this episode has taken us to the edge of what's known and what's feared. Whether you see asteroid defense as an unfolding triumph of human planning or a house of cards awaiting the wrong rock, one thing is certain: our place in the cosmos is not guaranteed. Until next time, stay critical, stay curious,